All right, so Zener diodes. Zener diodes look like this, which is how you can differentiate them from regular diodes, because regular diodes are black, usually, with a little stripe through them. And they also have a different symbol. And the symbol for a Zener diode is this fella right here. I have never seen this before in my entire life on a circuit schematic. So it's this guy, right? And that is a regular diode looking thing. But then he's kind of got this arm down and this arm up, and he is shaking them all around, right? So normal diodes, you know that current will not, current won't flow in the reverse bias direction, but will flow in the forward bias direction. That's how a diode works. It makes them really useful for things like current rectification. You can also do funky things around signal clipping with them. They're cool. Now, if you get a regular diode and you try and, force a huge current through it in the reverse bias direction, it will eventually reach what's called its breakdown voltage, and the current will basically force its way through and fry the diode. And what will probably happen is that a little bit of the magic smoke will come out, and then the diode will no longer work. That would be bad. A Zener diode, on the other hand, a Zener diode is designed to actually conduct in its breakdown region without getting fried. And what this means is that when we're talking about a Zener diode, it's supposed to conduct backwards. That's its whole point. And to sort of explain that, I guess I'll make this graph a little bit bigger. No, I won't, because that seems like too much. So we'll just look at this graph. I hope that you guys can see this. Is that like clear enough that you can kind of make out what's going on? Beautiful. All right. So let me change my pen, if I can. Yes, to verify. Beautiful. Okay. So here's a graph of how a Zener diode behaves. So over here on this side, we have its forward bias sort of region. This is, to say, this is what's going on when the current is moving through the Zener diode in the forward bias direction. Here we've got on the y-axis, we've got our current. And here on our x-axis, we've got our voltage. Now, a diode has a voltage drop of between 0.3 and 0.7 volts. What that means is that across a diode, you'll normally measure that sort of voltage drop. It also means you've kind of got to supply that much voltage to the diode to get it to actually start conducting properly. And you can sort of see here, until you get that diode to 0.7 volts across it, it doesn't really kick off in terms of letting all of this current go through. But once you get to 0.7 volts, all of that current can kind of flow through really nicely. So that's the forward bias region. That's not different really from a regular diode. What is different is this reverse biased region. So this is current flowing through the diode in the opposite direction. Now, for a Zener diode in the reverse bias direction, there's something that's really important to it called the Zener current. So that's IZ, I for current, Z for Zener. And that's the minimum. And that point is about here on our graph. And what this is sort of showing you is that you have to get a certain current flowing through that diode in the reverse bias direction before it will actually start allowing current to really flow through. But once you get to that region, which is your IZ minimum, it conducts pretty much, at a regulated voltage, or at, a fairly buttoned down voltage. So if we looked at this, once you hit IZ minimum, the voltage sort of stays at this, what we call the Zener voltage, and that's VZ up here. And it stays in that region, which is pretty close to its rated voltage, until you get it down to IZ max. And if you get a Zener diode above IZ max, what do you think happens? Come on, audience participation. The magic smoke comes out. So the magic smoke comes out, and your Zener diode would be toast. But there's this, region in the middle, which is really, really useful to us. And the reason that it's really, really useful to us is because you can use it to do some really important things. So let's say we've got a voltage supply, and it is Vs, and let's just say that it's coming out of, I don't know, a 9-volt battery. So we've got a voltage supply that is at 9 volts. And we've got something over here, alpha load. We've got something over here, and it's only rated for 5 volts. Right? Now, if we just hook that straight up to 9 volts, it might go pop. And so what we can do is we can use a Zener diode in this situation to actually, control the voltage or regulate the voltage to 5 volts so that our thingamabob works. And so what we would do is we would put a Zener diode in here like this, and we would connect this to our load, and we choose a Zener diode that was rated for 5 volts. You can get Zener diodes in many, many different ratings and many, many different flavors. You can get ones that, do all the voltages that you could ever desire. We've got some of these coming into class. They are currently shipping from Hong Kong. And so when we have some of them, we might, do a quick demo on them just to see that, yes, they do actually behave in the way that we sort of described. Okay, so we've got a circuit, but we haven't finished it. Now, we have got to get this Zener diode to behave properly, we've got to get it above IZ minimum, but we have to keep it below IZ maximum. And so if we're trying to do that, before we connect, our 9-volt power supply to our diode, what do you think would probably be a nice idea to have somewhere in that current path? Let me ask it another way. If we just connect this wire or this trace to this diode, what's the current likely to be through that diode? Is it likely to be really high, really low? Is it likely to be a delicious French press with a dash of milk? Is it likely to be a pineapple? It'd be super, super high. Yep, 100%. So if we, if you get a battery and you connect it through a diode, that's a very big current because diodes don't have a lot of resistance. And we know that, Ohm's law, V equals IR. So current is equal to voltage divided by resistance. So if we would do this maths, we would say that we've got 9 volts, and we would say that we have a voltage that is very, very close to 0. And if you divide, this by 0, then our current is infinite. And in reality, we know that, diodes have a little bit of resistance, and so this would be a very, very low number, but this would still be a very big current. And so that would be very, very bad for that diode. So how do we control current? How do we, make sure that the current flowing through this diode is stepped down a little bit? Beautiful. Yeah, we just add a resistor. And so you will always see, or you should always see, if you want it to work, you should always see a, let's just see if I can, can't rub that out. You should always see a series resistor in line with a diode, with a Zener diode rather. You should probably see one in with a diode as well, but whatever. Now, what we would need to do is we would need to choose a value of this resistor that is low enough that the current that flows through that Zener diode is above IZ minimum, but high enough that the current that flows through that Zener diode is below IZ maximum. And that's probably quite a wide range, right? But it is important to sort of pick a resistor value that's going to at least make the diode conduct properly, but not fry it. And if you do that, then a magical thing happens where current flows through this diode in such a way as to actually control the voltage that we see here and here. And therefore, it's the same voltage that we see here and here. And if that, Zener diode is rated for 5 volts, then we see 5 volts across this load, and this load is very happy because it is receiving its rated sort of voltage. And that is, in essence, how Zener diodes work. It's what they're used for, and they do that job really, really well. The other thing that you will see them, or the other situation that you will see them used in, is used in bridge rectifiers, and I'll show you a quick example of how you would use one in a bridge rectifier as well. I just have to grab a picture. And we go this one. Oh, no, wrong. And I just need a nice picture of a bridge rectifier, or even a bad picture of a bridge rectifier, I'd accept. Nope, nope, nope. I guess that'll do. There we go. It actually made it. Okay, let me zoom in on this a little bit. We'll make this a little bit bigger. Okay, so we've got a bridge rectifier, and we can see that in order to make nice current, or to make nice DC current, this bridge rectifier is actually missing something straight off the bat. Can anybody, for a bit of revision-y goodness, tell me what is this bridge rectifier circuit missing if we don't want terrible lumpy DC? It is missing a capacitor. Beautiful. So you chuck a capacitor across like this, and that's going to do the thing that capacitors do, which is it's going to, when when the voltage is increasing, that's going to charge the capacitor, and when the voltage is decreasing, the capacitor is going to discharge, and that is going to turn this really lumpy signal into something that looks a little bit more like this. Ripple, ripple, ripple. You'd have 3 ripples, right? Anyway, cool. But the point is, this has still got a bit of a ripple, which we don't like. And let's say, just an arbitrary sort of value. Let's say that this ripple at its peak is 12 volts. And let's say that what we're looking for, what we want, is actually 10 volts. Then what you can do is you can put a series resistor here, and you can put a Zener diode here that is rated for an output voltage of 10 volts. And what that does is it regulates the voltage at a level, well, at the 10 volt level, that is below the level of our ripple. And so this load now sees a much smoother sort of 10 volts because you've kind of cut off the ripples. And this is, another situation in which you will see Zener diodes used. So just as like an arbitrary example, let's come back up to this example here. And let's say that our Zener diode here has an IZ minimum of, I don't know, 20 milliamps, and it's got an IZ maximum of, let's say, 1 amp. Nice wide rating there. Nice wide range sort of there. What sort of value resistor would you pick so that this Zener diode behaves in the way that it's supposed to, so that it conducts? Or how would you you'd use, what formula would you use to try and figure that out? It's not a trick question. It's not a trick question, guys. It's this one. If I'm ever asking you to use a formula, it's normally Ohm's law, because that's sort of the big one. And it's the big one that keeps popping up in all of these exam questions. They're all really elaborate ways to ask you to use Ohm's law. Okay, so you need to use Ohm's law. And we don't know, in this situation, we don't know the resistance of our load. And so what we want to pick is, we want to pick something that is, going to mean that, even if we put a decent sized sort of load in here, we're still going to get above 20 milliamps, because we want this thing to conduct, but we want to keep it, away from being 1 amp. So why not just pick a number that's in between the two? So 20 milliamps is 0.02 amps, unless I'm mathing completely wrong. And so let's just say that, like, our ideal sort of current is, I don't know, 0.5 amps. And let's just treat it like a simple series resistor question with only one resistor. And let's just say that we are looking for, so V equals I R, but we're solving for resistance. So resistance is equal to V divided by I. And we know that our supply voltage over here, which is the one we care about at the moment, that is 9 volts. Our ideal current is 0.5 amps. And so our perfect, or our resistor value in this situation, that's going to make that work, is going to be 18 ohms. So an 18 ohm resistor. So that would make that work. That would make that work just fine, because what you'd find is that you'd have, about half an amp of current through this Zener diode. And from these numbers here, we know that that's nicely somewhere in the middle of its, happy to conduct without being too limited or having, getting too hot and having the magic smoke come out. And so that's how that works, right? So